Let us talk about near real-time solutions for online string problems. So what is it about? It's not about offline algorithms, where an offline algorithm first needs to read the entire input and then computes the solution of it. Here we are interested in for computing the solution for the part read so far. In the world of strings, what you have is you have read a prefix up to the ith letter, and then you want to compute solution for the current input for this prefix. And afterwards, a new letter arrives, you update your string by appending this letter, and then you compute the updated solution. So for every of these prefixes, you want to compute a snapshot of the solution, which by snapshot I mean not an approximate solution, but the complete solution of the prefix read so far. And this is what online algorithms are all about. So we want to incrementally update our solution as new letters arrive. Among online algorithms, the most common algorithms are just analyzed in the amortized sense. So you analyze the time complexity with the whole time for the entire input. And often you neglect worst case times per letter, which can be high. And for instance, in this plot, you have these spikes for the yellow line. And in certain cases, you don't want them. And there is on the other line a very restricted subset of online algorithms called real-time algorithms, where the worst case time per letter is bounded by a constant. So this is a red line, which is just a constant. Here we are a little bit more relaxed, which we call near real-time algorithm, which exchanges the constant with a poly-log-log time bound in the input size. So what you get here, it's a small decay with respect to the read input so far. So for real-time algorithms, in working with strings, we have seen pattern matching, palindrome recognition, and some Laplace 78 live factorization. But for near real time, which we don't have for real time, is the suffix reconstruction, which we use here in the talk by having this title, which is based on Weiner's algorithm. So we first focus on what this algorithm is. So the idea is that you have as an input a text from length n, whose letters are based on an integer alphabet, sigma. And here the letters arrive from right to left. And we assume that the last letter is a unique terminal symbol. So the goal is of Weiner's suffix reconstruction is to construct the suffix tree, st, of your text. And we construct it from right to left. So you construct it for the j's suffix from a j plus 1's suffix by adding the j's letter in front of this one to get this one here. Okay, as an example, we have this string. And the first thing is we have the suffix tree of dollar, then a dollar, and a dollar, and so on. Now what you can see is that for each update I mark the new created edge in green, and the longest common prefix of the new suffix we have inserted with all already existent suffixes in red. For instance, here for adding AAB, the AAB shares with a dollar just a. So this one is the red pass. It could be many edges, it could be none. So basically here the BAA doesn't share with any of these prefix, so there is no red pass. And the idea is that this red pass is where we branch off to create the green edge here. And this is this branching off, this is called the insertion point. And the naive solution to find the insertion point is to do just a matching starting from the root up to match the new suffix we want to insert. So we go down to this path and find the insertion point. So assume that the suffix you want to insert is abcx, and it happens that ABC is already downwards represented by a node, so the locus of ABC is this node beta. Then if there is nothing with x, then we just branch off here and write here the x and create here a new leaf. But if it happens that the suffix we want to insert is just abx, so without the c, then we have to branch off within this edge. So we have to branch this, split this edge, create a new node, let's call it delta, and add here the remaining part of the suffix, which is just x, and create here the leaf. So in any of these cases, 2 or 3, we call the branch of locus the insertion point. The key observation is that each suffix is represented by a leaf, which you can just number by the starting position j, which usually do, and call it suffix number. And the goal to update the suffix tree by prepending one letter is to insert this new leaf for the new suffix. And for that we need to find the insertion point, and then the leaf insertion is easy then, it's just constant time. But finding the insertion point is hard. This is a problem stated here formally. And this locus is, like I explained, it's the longest prefix of the suffix you want to insert that already appears in the already indexed part of the text. And if we call for this problem the time complexity TSU, then there are a bunch of solutions already known. So if you do it naively, just going from the root downwards to find the insertion point, you need order n time per suffix tree update, which is very costly. But Wine already found out that you can do it in log sigma time amortized, and if you follow this line of research, you find here time complexities which are in our time budget of near real time. So we can use one of these approaches downwards to get a near real time complexity which we want to achieve. And the question is now, if we use that, we can get the insertion point for free in this time bound, but what can we do else? So what it does, it like in the problem statement, the insertion point, it gives us the longest common prefix between the new suffix and the already stored suffixes. So it's basically the longest common prefix with the lexicographically closest one, which is either the predecessor or the successor. So we can solve the following problem, that we can compute the longest repeating prefix of the already read part and can update that online. Just outputting the length is easy by just using the insertion point. So the algorithm works as follows. Whenever you want to compute the insertion point, you have to follow the red path. And let's say you branch off with ABC. So it's the first case where you don't create the insertion point, it's already there. And then you just output the ABC, the length of it, because that's the longest common prefix. On the other hand, the second part is that you have to split the edge. Then the new created node is the insertion point, and the string label, the length AB, is the answer you want to report. Okay, that was very straightforward. And what you can do with that is to compute the so-called LRS array. The LRS array builds on the longest repeating prefix idea, that you want to compute an array of the same size as the length of the string. And for the chase position, what you want to store is the length of the longest suffix of the chase prefix that occurs at least twice in this chase prefix. This problem is not a toy problem, it has been studied, but of course you can do better in near real time, which is this work about. Okay, the main problem is that we don't have here a prefix but now a suffix. And because if you read text from right to left or left to right, it changes suffix and prefixes. And that's basically what we do. We read the text now in reversed order. So we reverse the text in this fashion. And what happens, we get actually usual online algorithm that reads the input from left to right. Because we flip the input around and do the right to left construction online. So this gives us online algorithm for computing LRS in left to right sense that just takes exactly this TSU worst case time per letter. And that's all. This is actually just based on a previous work and just plug in the time complexities. So if we have LRS, then what we can do is compute the Lamplessive factorization. So here we use the Lamplessive factorization without adding a new character, which basically works by scanning the text from left to right. And first, new letters, we just output them literary because they don't have any previous occurrence. But then we try to encode string by the longest possible previous occurrence with a back reference. And overlaps are allowed, like here for ABA, we can refer here, and this source overlaps with length 3 with the A here. So overlaps are allowed in this LZSS factorization. Okay, so for this factorization, there are also known bounds, but of course you can do a little bit better with near real time per letter. The idea is that you use the suffix tree construction, and suppose that we have already computed the factorization up to the third letter so far. So we know that the next factor starts at the fourth position. And for that, what we have to do is that we have to track the lengths, the longest possible lengths you can generate for the next factor. Because if we have the length of the next factor, we know where the next one will appear. So this is all about that you want to compute the lengths. Okay, so let's fix p equals 4 for p is a position where the next factor will start at position 4, but we don't know yet its length. So in this case, we have already built the suffix tree up so far. And what we do is we just prepend a new letter and we query the insertion point for its length. So this is the red pass, and we count the number of letters in the red pass. So we have added one character, and we ask, can we refer to a previous A? Because this is just one A, and yes, it happens because the red pass is of length 1. So we can actually accommodate here a factor of length 1. And we continue, and we query again, and the pass has length 2. And so we can accommodate a factor of length 2 because BA appears previously. And the same also for ABA. The ABA already appears here again. So this is also possible to create here a factor of length 3. And we continue prepending the next letter. But now what happens is that the pass, the length, the number of letters, it decreases in the number of letters. So this basically tells us we want to have now 4 letters, but we get only 2 here. So we have to stop. So what we have done, we could accommodate a factor of length up to 3, but 4 is not possible. So we stop at length 3, and we know where the next factor will start. And that's all for computing the LCSS factorization. Okay, so we have the LCSS, and if we add one new ingredient, the shortest double suffix, we can get also the minima unique substrings, also called mus. So what are mus? So given a substring LR of your input string. It is called a mus if it occurs exactly once in the text. But if you remove the leftmost or rightmost character, then it occurs at least twice in the text. So assuming that it's length of at least 2. Then we use this notation for the set of all mus, which we want to now to maintain online. So example for a mus is AABA, because you can see this AABA in the red bar, it occurs only once. But if you remove the rightmost letter, the blue one, it occurs twice. Or if you remove the first letter, the green one, the green bars too, so they also occur twice. If you look closely to this picture, you can find other mus like BAB or BAA, which are in this pale red color. Okay, and we want to maintain the mus online, so we read the text online and we update the mus. This has already been studied, online computation, but again it's just amortized, and we can get again near real time in the worst case per letter. But then we use also a so-called growable array, which allows us to, this is basically an integer array of n integers, and we are allowed to grow the incremental size of the array and have random read and write access to any arbitrary entry, which you can find in textbooks with doubling technique, but this is also just amortized. But with technique from Brodnik and colleagues, it's worst case time, constant worst case time per operation. So what Mieno and others do, and what we also use here, is that they showed how to update the set of mus when a new character, a new letter arrives. And for that, I need the so-called shortest double suffix, SDS, which is a suffix of your text, which exactly has 2 occurrences in the text, so one as a suffix, but somewhere else. And this SDS may not exist. But if it exists, then we want to maintain it. So the idea is, so shown in this paper, that they classify where the mus appear. And for that, they use the longest repeating suffix, again, which we can already compute. And you assume that you have now read the text up to the j's letter so far, and then the j plus 1's letter arrives. So you compute the new LRS, and here if you assume that this one is of this length, then if you prepend a character, then by the definition of the LRS, because it's the longest one that is repeating, then it doesn't repeat anymore. So it could be a mus, so you have to check this range here if it's a mus or not. And this one could be a former mus, which you could delete. Okay, here in this setting I have not drawn the SDS in the case that if it doesn't exist, then we are already done here. These are the 2 cases we have to consider. If the SDS exists, then it's a little bit more complicated, because here assume that the SDS exists, then it appears somewhere else. And we have to take care because this one could be a former mus, because if we have not yet the j plus 1's character, the double occurrence, this one vanishes, and it could have been a mus. So we have to check whether you have to delete it. This is again like in the former case, the LRS could be a mus now. And then we have 2 mus candidates to consider. So if we go from this one here to the right, it could be now a mus. Or we can get from this LRS occurrence to the left by adding 1 character, and it could be a mus. So we have two new mus candidates. This one is like in the previous case a mus. So we have to check these cases. But this basically boils down to maintaining LRS and SDS. LRS I have already shown, and SDS you can very easily compute with having the insertion point. So the SDS in the reverse setting, because we index in reverse, basically flips the suffix to a prefix, and we want to find basically the one that has again an occurrence that is not a prefix if we index the reverse string. But this is easy to spot, because if the insertion point is an already existing node, like in this case here, then the 3 here, then you know that it has at least 3 leaves, which means there are 3 occurrences, so it cannot happen that there is an SDS. Otherwise, in this setting, that you branch off at an edge that goes to a leaf, like here, the node 7, you know for sure that it has 2 leaves, and therefore there is an SDS. For instance, in this case, the BA just appears twice, so the BA is a SDS. Otherwise, if we branch off somewhere, when we don't go to a leaf, then again, with the same reasoning as before, the SDS cannot exist. Okay, and that gives us already the final theorem that we can maintain the mus online, also in the time complexity for the suffix tree update in Weiner's machinery, in the worst case time per ledger. Summary is, unfortunately, the real-time suffix tree construction remains open, but there are near real-time solutions. And if we use any of them, then we can compute many applications in near real time, just using the insertion point idea. There are other problems we have treated within the same time complexities, like reversed LC factorization or the sufficient sets. Okay, and that's all. So any questions are welcome.